All right, Year 12, welcome to week 6, term 2. And our work on vectors continues. We're going to start with a little recap. I'd like you to answer this question, so I want you to pause the video, do the question, come back, find the vector equation of the line passing through these 2 points. 3 dimensions, we're just after there's a line that goes through them. I want the vector equation of the line. We're going to turn that into its parametric form, and then its Cartesian form. And so do all that, put the 3 forms in, and then come back and I'll go through my solution. Okay, so first thing we find out is a direction vector, AB, by just doing our subtraction of components. We get 1, 2, 1. Now, we can then write our vector equation. So this is our vector equation here. So this is our vector equation. It's already done. It's in this form R equals, now 1, 3, negative 1, that's a fixed point. We could have used 2, 5, 0, doesn't matter. So that's why when you pose these questions, it's find a vector equation rather than the vector equation. Lambda to allow for different lengths. So you can have a scalar here, but this 1, 2, 1 is our direction. So and that's taken from our AB vector. So R equals this. Now, in order to unravel the Cartesian equation, we split R into X, Y, Z. So therefore we get X, I'll get back to my blue pen, X is equal to 1 plus lambda, Y is equal to 3 like so. From that those 3 equations, we make lambda the subject, and from those 3 equations we get our Cartesian, which I'm going to write like this. Now, if we're just representing our Cartesian equations, you wouldn't do this, but I want to point out a couple of things. From this format here, we can see what we can see from our numerators what a position vector is. So we can say therefore, all right, so we can pick off our position vector. So I'd say therefore from numerator we can pick off our position vector, a position vector, which is 1, 3, negative 1, 1, 3, negative 1, or a point that's on the line. And from the denominator, very importantly, from the denominator, we get our direction. Now I should write this as a vector. 1, 3, negative 1, and our direction vector being 1, 2, 1, which is why I wrote it in that format, put it over 1, that sort of thing. 1, 2, 1 comes from ABC. That's done full circle now. So there's a bit of a recap, important because we're going to draw on some of this stuff for our next piece of work. And our next piece of work, our next heading is the equations of planes. So let's take that heading down, equations of planes. Perhaps before we do this in 3 dimensions. Oh yeah, that's fine. Yeah, that's good. So hopefully you can see there, by making lambda the subject, you can see why our direction vector of 1, 2, 1 comes from this, because of our coefficients of lambda are our direction vector. So 1, 2, 1. So when we make lambda the subject, they turn into the denominators, and the position vector sits out the front there. So don't know what happened to my heading just now. So equations of planes. Now we often use, for equations of planes, we often use the symbol pi, P for plane. So if you see pi used That's quite often the case. Pi, if you're talking about more than one plane, it might be pi subscript 1, pi subscript 2, that sort of thing. So there's our heading. Let's start to have a little look at how we do this, equations of planes. And I think we'll kick off with an example. So it's from the textbooks, and I'll just write it out now. Okay, so we have a plane with these points on it, A, B, and C. Okay, so we've just got some plane here, and we've just got the points A, B, and C on the plane, and we are now, so we're after non-collinear points here, A, B, C. We can then find our equation of the plane by establishing, just as we did with equations of lines, finding direction vectors, and we already have our position vectors, so we can write out our vector form once we've got a little bit of information about our vectors on that plane. So let's get some information. We can say that AB. Let's get AB firstly. That direction vector going from A to B, we are going down 2. We're going from 0 to 1, so that's up 1, and we're going from 1 to 0, which is down 1. We can get AC. Again, we've got choices. We could take BC, but we tend to just go with AB and AC. 1 to 0, negative 1. 0 to 1 is positive 1. 0 to negative 1, minus 1. So there's our AB and AC. So I looked at my B component Z rather than my A component Z there. So that Z component of AC goes from 1 to negative 1, so that's minus 2 there. Okay, so two direction vectors. We can now produce our equation in vector form. So therefore, R is equal to, take a position vector. We'll use 1, 0, 1, 0, 1. Just take the A point, and now we've got two direction vectors. So we use two parameters, alpha for our AB, negative 2, 1, negative 1, and beta for our AC, negative 1, 1, negative 2. So we have already our vector form. So we've got our vector form of plane ABC. Okay, so that's terrific. We'll move now to finding the parametric form of the line, and the parametric form is just going to be extracting x, y, and z. So R becomes x, y, z equals. So we take x will be equal to 1 minus 2 alpha minus beta. Y is equal to alpha plus beta, and z is equal to 1 minus alpha minus 2 beta. So here we have our parametric forms, and so parametric form. Okay, now moving to Cartesian form, we've got a little bit of algebra to do, because to eliminate alpha and beta here, there's a little bit more to do than we had in 2 dimensions. So our job firstly will be to make, to eliminate one of the parameters from all 3 equations. Now the way we can do that is just work in pairs. So all right, I better label my equations 1, 2, and 3 so I can refer to them. 1, 2, 3. So what we'll do firstly, let's eliminate. What does it look like? We can eliminate comfortably. I can add 1 and 2, and B will go. So I'm going to eliminate B. I'm going to eliminate beta. So that'll be done by taking 1 and adding 2. That's how I'll get rid of it in the first 2 equations. I'll then have to use another elimination method to get rid of beta from 3. So we're going to eliminate beta from all 3 equations. So 1 plus 2 will get me started. And in doing so, I get x plus y is equal to, okay, so I'm adding, I got 1, I got the betas are gone, 1 minus 2 alpha plus alpha. So I get 1 minus alpha. Okay, so that's my that's now my equation 4. Now, how do I get rid of beta from equation 3? I could say multiply equation 2 by 2. So I'm going to say 2 times equation 2 plus equation 3. And we'll get rid of beta from the third equation. So we will end up with 2y plus z on the left-hand side. Right-hand side, multiplying by 2, remember, I've got 2 alpha. My 2 beta is going to cancel, so I've got 2 alpha minus alpha, so that's just alpha, alpha plus 1. So now I call that equation 5. And now, so I've eliminated beta. I'm going to write that in a different color because I think I'd like that to stand out a bit. So I'm going to eliminate. Now we could have eliminated alpha at this point, but we eliminated beta. So now I've got 2 equations with x, y, z, and alpha. So now in my second stage of making my Cartesian form of the equation of this plane, I'm now going to make alpha the subject. That's not alpha. Is that alpha? Yep, alpha the subject of 2 remaining equations. Okay, so if I'd eliminated alpha here, I'd make beta the subject of the 2 remaining equations. So let's have a look at what we get. So from equation 4, we get alpha equaling 1 minus x minus y. And from 5, we get alpha equaling 2y plus z minus 1. Okay, so I can now take these 2 equations, and so therefore I have equation 6 equal to equation 7. I've got no parameters, so I've just got Cartesian coordinates left. So therefore 1 minus x minus y equals 2y plus z minus 1. I put in alphabetical order, ax plus by plus cz equals d format, and I get, I'm going to push my x across, I've got a minus y, so it'll be x plus 3y, and I'm going to, I've just got one z there, just trying to organize all this information, and I've got 2 on my right hand side, x plus 3y plus z equals 2. That's my Cartesian form. Cartesian form of my plane. Beautiful. So now I've got an equation that describes every x, y, z point on this plane here that contained a, b, and c. Okay, let's do a little bit of investigating now, because that's quite an important result, and it does contain some interesting things. Now, if we look at the, how should we look at this? Okay, we might just, I'm going to have a look at, let's do this. Okay, I want you to now pause and work this out. I want you to work out the cross product of AC, right? The vector AC. I want you to cross AC with AB. Okay, so I want you to work out what AC times AB is. And before you press pause, think about, right, we're going to get, it's a cross product, it's a vector product. We're going to get a vector. What does that vector represent? I want you to think about what that vector represents. Before you go and find it, think about what that vector represents. Then come back and let's have a little talk about the results. Okay, hopefully you established in your own mind that the vector that this represents, this cross product, represents the vector that is normal to both AB and AC. Now, AB and AC both lie on the plane ABC, so it would be a vector that's normal to that. It would be a vector that's perpendicular to that plane, going either coming up from it or going down through it, and we're going to call that vector N. Let's just have a look at what you got for AC times AB. All right, I'm going to replicate your results here. All right, so I'm going to say now AC times AB will be the vector, or a vector, perpendicular to the plane. So we call that a normal, which we're going to give a little n to, a normal vector to ABC. Okay, so let's do AC times AB. Right, so therefore, AC times AB. That's going to be, okay, let's have a look here. We've got, is it -1, 1, -2? -1, 1, -2, crossed with -2, 1, -1, -2, 1, -1. Okay, so that's equal to, rule out my top row, so I got 1 times -1 plus, minus, sorry, let's just do this. 1 times -1, so that's -1, and then I subtract -2, so I'm going to be +2 there. Okay, rule out my middle row, go in the reverse direction. -2 times -2 is 4. Subtract the product of -1 and -1, so I'll subtract 1. Okay, and my last row, I'll go back to my regular routine. I'll go -1 times -1 is -1. I subtract -2, so I'm going to add 2. So the result is, I'll keep going across here, my result is -1 plus 2, so I get 1. 4 minus 1 is 3. -1 plus 2 is 1. 1, 3, 1. Okay, now let's have a look at, I want to match off this 1, 3, 1, this vector here, with my coefficients of my Cartesian form of the equation of the plane. Let's go have a look. 1, let's have a look. We've got 1, 3, 1 against 1, 3, 1. So the coefficients of my Cartesian form of the equation of the plane match the normal vector to the plane. Now that's a pretty powerful result, and we need to formalize that. Okay, so very important result, just written down here. Therefore, the vector whose components are the coefficients of the Cartesian equation, so the vector whose components are the coefficients, so the coefficients of the Cartesian equation, x, y, z coefficients, in this example 1, 3, 1, those components 1, 3, 1, they form the normal vector to the plane. The normal vector to the plane. So 1, 3, 1 is my normal vector. 1, 3, 1 to the plane with A, B, and C on it. Now let's just verify that. Have a little play around with that. That means that my vector AB, if I dot my vector AB with n, I should get, what should I get for dot vector? Dot product. If they're perpendicular, remember dot product is a measure of parallelness, so perpendicular vectors will dot to 0. So let's just check that that's the case. So my AB vector, I've just taken AB, -2, 1, -1. I dot that with my 1, 3, 1, which is my normal vector, and I should get 0. Negative 2 times 1 plus 3 minus 1, and that gets me 0. Of course I got 0. Now if I chose BC, I haven't used BC yet. Let's try BC. Let's try BC and dot that with n. So BC, well, BC is going to go negative 1. From 1 to 1, it goes 0. And it goes from 0 to negative 1. So it's negative 1. That's my BC. My 1, 3, 1 is my normal vector. And so I'll be able to do this for infinitely. All the vectors on my plane should dot with my normal vector to get 0. But this is nice just to verify. Minus 1 plus 0. That doesn't look right. That's actually this BC here. I've gone negative 1 to 0. That's positive 1 there, isn't it? My apologies. So this is 1 plus 0 minus 1, which of course gives us 0. Okay, so you get the idea. So this 1, 3, 1 is our normal vector. Now, why are we getting this to be the case? Why are my coefficients, my Cartesian form, why are they equal to my normal vector? Well, let's just have a little look at how this works. So if I've got a plane, okay, and I've got perhaps, okay, and here's my normal vector to the plane, just coming out at right angles. There's my normal vector. Okay, I'll just call him ABC. ABC. All right, why am I calling them ABC? No accidents there. I know they're going to be I'm anticipating they're my Cartesian coefficients, right? So AX plus BY plus C equals AX plus BY plus CZ equals D. So I'm just giving them those names. Then I'm going to have a look at a couple of points in here. So maybe here's a fixed point here, X naught, Y naught, Z naught, and then just another point on my plane XYZ. Now, if I have a look at the vector that joins these 2 points, and I'll just get my ruler out so this looks sensible. So the vector that joins these 2 points, just line that up. That vector there, go the other way, sorry. We'll go this way. So that vector, I know that this vector is perpendicular to my n. So this is, you understand, I've set up a plane here with a general point, a fixed point x naught, y naught, z naught, a general point x, y, z, and normal vector ABC. So from the definition, I know simply this, that the vector that goes x minus x naught, so I know that my vector x minus x naught, y minus y naught, z minus z naught, that vector there that I've just drawn in, that vector dotted with my vector ABC, which is my normal vector, I know that has to give me 0. Okay, now if I expand this guy out, do the dot product on it, so therefore I'm going to get x minus x naught A plus y minus y naught B plus z minus z naught C. That's all going to be equal to 0. Okay, if I tidy this up, I will get AX plus BY plus CZ equaling, on the other side of the equation, AX naught plus by naught plus c z naught. So let's just now test this result. I'm going to put a border around this because this looks fairly momentous. This piece of work here. It's that one there, isn't it? So let's use that. All right, now that's the general result, isn't it, for the equation of the plane? So let's just test that that works on the equation that I've just come up with. So test. Okay, so I should get ax plus by plus cz. That's just generalized. Ax plus by plus, sorry, I know what my a, b, and c are. A, b, and c. So for n, which is my ABC, which is in this case my normal vector. What do I work it out to be? 1, 3, 1. So I've got my normal vector at 1, 3, 1. I need an x naught, y naught, z naught, so that can be any of my points. Let's take just a 1, 0, 1, and a at 1, 0, 1. Therefore, my equation, the equation of plane ABC should be, all right, so A is 1, so it's x, B is 3, so it's x plus 3y, C is 1, so that's just x plus 3y plus z, equals, now I'm doing ax naught plus by naught plus c z naught, so A 1 times 1 plus 3 times 0, so I'm on 1 plus 0 plus 1. So therefore, x plus 3y plus z is equal to 2, which seems to match up nicely with, or where was it? Right here, with my Cartesian form right here. X plus 3y plus z equals 2, x plus 3y plus z equals 2. So with a normal vector and a given point, I can find the vector equation of a plane without going through all my my vector form, parametric form, and my simultaneous equations. I can just get straight there just using this information here, that my normal vector ABC will dot with a vector on my plane. All I need is a point, because I can form a generalized vector with x minus x naught, y minus y naught, and z minus z naught. I can dot it with my ABC to get 0, and I get this lovely format here. And we should do an example of that. Okay, example. Find the equation of the plane pi, which contains this point and is normal to this vector here. So all we need is a point and the normal. If we don't have the normal, we can get it. As long as we've got 3 points, we can form 2 vectors from. We can cross them to get that normal vector. And once we've got that normal vector, we can again use it, because now we've got 3 points. We can use it with our newfound knowledge about how to form that equation of the plane. So pi is going to be equal to, so what do we need to do? We need to say that pi, right, so it's going to be ax plus by, so my normal vector, so maybe I should just write my normal vector first. My normal vector is my coefficients here of my base vectors, 2, -1, -1. Okay, so that is going to help me with a being -1, 1, 2 to get pi, which is 2x minus y minus z. So the coefficients there have come from my normal vector. That's going to equal, what is it going to equal? Well, it's going to equal my dot product of the normal vector with my point A. So see what it read up here? Ax naught plus by naught plus cz naught. Ax naught, 2 times -1 plus -1 times 1 plus -1 times 2. So 2x minus y minus z is equal to -5. Therefore, 2x minus y minus z is equal to -5. Okay, hence show that the point 0, 4, -1 lies on the plane. So therefore, put 0 in for x, so 2 times 0. Put 4 in for y, and -1 in for z. And we will get 0 minus 4 plus. Okay, so I've just discovered a mistake with this question. This point does not lie on the line. So in order to make it work, we're going to have to change that -1 to a 1. So let's just fiddle that. That's a 1 there. And therefore, what we would get here is we're just subtracting 1. And so we'd get -4 subtract 1, which is -5. Satisfies the equation. So you'd say, therefore, the 0, 4, 1 lies on pi. And we're done. Okay, I think exercise 11M is yours for the taking.